Hello everyone, my name is Ali Zolkadar. I am a PhD student at the Department of Chemical Engineering at Tennessee Technological University under supervision of Professor Bernanke. Today I'm going to talk about equation of state on the basis of molecular thermodynamics. First of all, we want to know what is equation of state and why is that important. The equation of state provides a mathematical relation between two or more state functions associated with the matter, such as its temperature, pressure, volume, or internal energy. In other words, the equation of state relates one thermodynamic property to another thermodynamic properties. In principle, you can do this with anything. For example, you can relate pressure with temperature and density, enthalpy with temperature and volume, or entropy with pressure and enthalpy. The most common combination is either pressure as a function of temperature and volume, or alternatively volume as a function of temperature and pressure. Now the question is why the equation of a state is important. Why we should be interested in equation of a state. The reason we are interested in equation of a state is because we eliminate using table and chart. When we want to design a process, we need to understand the physical state of our product in each part of process at dynamic condition. We should use equation of a state to calculate dynamic changes of physical properties of material, and this is just application in design of process. If we need to do optimization, we need to understand the state of product at many different conditions, and either it's time consuming or maybe it's not possible to use chart and tables instead of equation of a state. Also today, most of optimization have to have an equation of a state as an input. Another example is phase behavior of crude oil in petroleum reservoir. In petroleum reservoir, the temperature is almost constant in certain depth. However, the pressure changes during the production based on the flow rate and pressure. Estimation of pressure of reservoir are required at different depth of petroleum reservoir to control the wellhead facilities based on the crude oil properties. We cannot plot the phase envelope of the reservoir in order to obtain physical properties of crude oil at different conditions without using equation of a state. Now I'm gonna talk about development of equation of a state for gases. Early experiments on the behavior of gases were carried out by Robert Boyle in the 17th century. Boyle showed that for a given sample of gas at constant temperature, the product of pressure and volume was always the same. Here is the one sample of Boyle's law. The left container filled with gas particle, the pressure of this sample is low, which is 5 atmosphere. Since gas is compressible, we can put pressure on the piston and we can push it. And what eventually will happen after we increase the pressure, all the gases particles squeeze down into the much smaller area. So in the right cylinder, the pressure is 50 atmosphere. You can see as the pressure goes up, the volume goes down. That means pressure and temperature and volume have inverse relation at constant number of mole and temperature. Based on Boyle's law, if the P1 times V1 is equal to K and P2 times V2 is equal to K again, at constant number of mole and temperature, we have relation below P1 times V1 equal P2 times V2. Boyle's law is understandable from the picture of a gas as consisting of a huge number of molecules moving essentially independently of one another. The pressure exerted by the gas is due to impact of the molecule on the wall. A decreases in the volume cause the molecule to hit the wall more often, thereby increasing the pressure. But in actuality, the molecules of a gas exert force on one another, so Boyle's law doesn't hold exactly. But in the limit of zero density, which as the pressure goes to the zero or as the temperature goes to the infinity, the gas molecules are infinitely far apart from one another. Force between molecules becomes zero, and Boyle's law is obeyed exactly. We say the gas become ideal in the zero density limit. Robert Boyle noticed that heating a sample of gas caused some volume change, but he didn't follow up on this observation. About 1800, two French scientists, Jacques Charles and Joseph Gay-Lussac, began studying the experiment of gases with increasing temperature. Charles' experiments showed that the rate of expansion with increasing temperature was constant and was the same for all the gases they studied as long as their pressure remained constant. Charles' law showed there is a direct relationship between volume and temperature. Here is an examination of Charles' law. We put same amount, that means same number of mole of gas in the tube at two different conditions. The right side is a boiling water bath and the left side is the ice water bath. You can see in boiling water bath, the higher temperature, the higher kinetic energy of these particles, and they are moving around really fast and the volume of gas is high. But in cold water bath, which the particles have much less kinetic energy, they move slow and they don't need much room. Based on this experiment, we understand the volume and temperature have direct relation. As one goes up, the other one goes up too. Gay-Lussac show the relation between temperature and pressure when the volume is constant. Look at this example here. We have two cylinders of gas with constant volume. When we heating up, the temperature of gas particle increases, and what's gonna happen as we keep the volume constant, the pressure inside the cylinder is gonna increase immediately, depending on how much the temperature increasing. The pressure and temperature have a linear relationship as long as volume remain constant. As the temperature increases, the pressure increases too. We have direct relationship between pressure and temperature. There are three gas laws which we learned so far. They each assume some source of changes happened, and they tell us how two variable changes before and after the changes. In this three law, always we have two variables. Let's assume we want change pressure, temperature, and volume of this cylinder. We cannot use any of these three laws here because there are three variables in this problem. And in order to solve this problem, they came with combined law, which is combination of all of these three laws. The law it's P1 V1 divided by T1 equal P2 times V2 divided by T2. And they put all three rules in one law, so we can look at how these three variables respond to each other. Avogadro's law talks about relation between amount of gas sample and the volume of gas sample. Avogadro postulated that at the same temperature and pressure, equal volume of all gases contain the same number of molecules. He stated that at the constant temperature and pressure, the volume occupied by gas sample is directly proportional to the number of mole of gas. Here is an example of Avogadro law. You can see in figure A the number of mole for CO2 was less than figure 2, and the occupied volume for sample A is less than sample B. And this figure shows at the same temperature and pressure, equal volume of all gases contain the same number of molecules, which here is 1 mole for all gases, that is equal to Avogadro number. Especially 1 mole of ideal gas occupied 22.4 liter at a standard temperature and pressure regardless of identity of gas. Lastly, all the laws correlate on one equation called ideal gas law. Based on these three laws, we can tell as volume goes down, the pressure goes up. This means the pressure related inversely to the volume. We also saw that pressure and temperature are directly related. That means as the temperature increases, the pressure will increase too. And then we also showed that increasing number of moles of gas would increase the pressure. That means once we have more number of moles of gas and high temperature and less volume, we have more collision and the result is more pressure. If we put all of these laws together, we can see pressure is directly related to the temperature and number of moles, and temperature and inversely related to the volume. We can convert this relation to a formula by adding a constant we call R as constant, and that will give us PV equal nRT. This is important equation called the ideal gas equation, which is very useful equation, and we can do a lot of things with it. For example, if we know pressure, volume and temperature, we can calculate number of moles that are on the system, or if we know number of moles, pressure and temperature, we can calculate volume. And this is only true for any ideal gases. And the next kind of obvious question is, what is an ideal gases? What is ideal gas law? Ideal gas is one that obeys these three conditions. The first condition is there are no intermolecular forces between gases. The second one is the volume occupied by the molecules themselves is negligible compared to the size of container, and the third one is the gas consists of a large number of molecules which are in random motion and obey Newton's law of motion. In real world, ideal gases don't exist because they have interaction between particle, and the particle have some volume event. If it's not much, but they still have some volume. The real gas behave ideally when the temperature is high or the pressure is low, because at high temperature the molecules have a lot of kinetic energy, which means they have enough energy to overcome any intermolecular forces that do exist. And at low pressure we have ideal condition because the particles are so far apart that their individual molecules volume is insignificant in compared to the container. The most ideal gases have the weakest intermolecular forces. For example, among these four gases, helium actually is most ideal because it has no bonds at all. That is weakest intermolecular forces. Nitrogen would be the next because it is nonpolar. There is a London or dispersion forces. CO2 is nonpolar, but it has polar bond, and the least ideal would be water vapor because it is polar, it has hydrogen bonds and a strong intermolecular forces. In this example, as you can see, ideal gas condition become less from top to bottom. The weakest intermolecular forces most ideal gases Now, how we can correlate the ideal gas when we have real gas? As I said in last slide, at high temperature and low pressure, the real gas behave ideally because the particles are not close enough to interact with each other. We can use the ideal gas law under a standard condition, temperature at 0 centigrade and pressure at 1 atmosphere to solve problems and figure out how gas molecules behaves. Under high pressure such as 1000 atmosphere and low temperature, we cannot use ideal gas because the gases doesn't behave ideally at those conditions. To solve problems, let's see what happened and why breakdown. Suppose we have below cylinder, the right side at constant temperature and 1 atmosphere pressure with four molecules. In this system, the distance between two molecules is much larger than actual size of molecules by itself. We cannot use ideal gas law to approximate how this behavior, because if I think we can use ideal gas law to approximate how this behaves, because if the distance is enough, we can assume the volume of particle is small in compare with the total volume, and since they are far away, we can assume they don't attract with each other. However, when we increase the pressure, such as left cylinder, which the pressure is 1000 atmosphere at constant temperature, the volume decrease and you can see the distance between molecules become less than size of the molecules itself. Under this condition, the kinetic theory breaks down. Now the molecules are very close to each other. They are so close, in fact, that they are attract and repulse to each other. The forces that we talked about it before, that we neglected in ideal condition, now we have to take them to consideration. To better understand, let's look at the behavior in molecular scale. Remember, the ideal behavior means the gas molecules don't interact with each other. Only kinetic energy present, no potential energy. But at high pressure and very low temperature, there are molecular interaction because the distance between molecules are close. Let's look at the nature of interparticle interaction varying with distance the molecules. As you can see in this graph, we have Lennard-Jones potential versus intermolecular distance. The Lennard-Jones potential is calculated with this equation, 4E times sigma over r to the power of 12 minus sigma over r to the power of 6. In this curve, there are three important parts which we need to know. At the left side, as we move two molecules really close together, for example, by increasing pressure, they're gonna push each other. In other words, there's going to be repulsion as we move them further apart. Eventually, they are going to get to an area which is minimum potential energy. After this point, if we go to the right, at this zone, there are attraction force between two molecules. In this example, the attraction between two molecules will be happen when the distance is far from 1.12 sigma. Sigma is hard sphere diameter, and the attraction part in this curve is represented by this part in equation, the sigma divided by r in power of 6. As r approach infinity, the potential approach to the zero, which you can see in this line. This part of equation represents the repulsion part of curve, which is sigma divided by r in power of 12. As r approach to the zero, Of course, it cannot become zero. It's near to the zero. What happened? The potential approach to the infinity. This is Lennard-Jones potential and attractive force corresponding to negative potential energy and repulsing force corresponding to the positive potential energy is shown in this picture. Lennard-Jones potential show that there are two types of interaction. When the particles are far from each other, they experience attractive interaction. And when they are very close to each other, repelling each other. Okay, now we need to know what is the equation of state for real gases. Recall that for ideal gas, the pressure time volume of ideal gas system give you nRT. And notice in the real system and ideal system, the nRT remain the same. Because if we talk about same temperature, number of mole and R, for ideal and real condition stay the same. The only things that change in volume is volume and pressure. Because on some experiments, which I will talk about it in next slide, the pressure in ideal gases is higher than real gases. Also, volume of ideal gases is less than volume of real gases. So we need to add some number to pressure of real gas to get ideal pressure. Likewise, we need to subtract some number from real volume to get ideal volume. Van der Waals in 1873 modified the ideal gas equation to give the Van der Waals equation. He defined X and Y in above equation. The X is attraction part, which is n squared times A over V squared, and the repulsion part is n times B. The parameter A is measure of the strength of the intermolecular attraction, and constant B is measure of molecular size. N is number of mole, V is volume, and this is the parameters of Van der Waals equation. A and B are constant that depend of gas being used, so they're different for different gases. Again, the reason we add this part because P real is smaller than P ideal. Likewise, the reason we subtract this from V real is because V real is larger than V ideal. And this formula is known as Van der Waals equation. Let's look at three scenarios for gases in a piston. First of all, at low pressure, we do have a gas comfortably on the container. In this condition, actual volume is equal ideal volume. In second container, we increase the pressure and decrease the volume. We squeeze those molecules together to medium and high pressure. As the volume decreases, some molecules are gonna stick together, and the ideal pressure, which is calculated by ideal gas law, is higher than real. In this case, attraction dominates. In last case, if we go to a ridiculously high pressure, you can see it actually does takes the gas does take up some space. With the ideal gas law, we make that assumption the gas don't take any space at a very high pressure, but they actually do. The actual volume here, it would be higher than what we would get with ideal gas law, and what we see at the real high pressure, repulsion dominates. In this slide, I'm going to talk about compressibility factor. If we want to detect deviation of the gas from ideal gas, we can use something called compressibility factor. Z, which is compressibility factor, is equal pressure times volume divided by moles times R times T. When Z is less than 1, intermolecular attraction exists. As you can see in the graph, when Z is equal 1, that is perfectly ideal gas behavior. When Z is higher than 1, repulsion is gonna start dominate, and when Z is less than 1, we would say the attraction dominate. The graph shows for all of gases at low pressure, they behave ideally. As increase the pressure for nitrogen and helium, there is just repulsion. However, for methane, carbon monoxide, and hydrogen, first there is attraction, and after some pressure we see repulsion dominate. The repulsion part doesn't make any big difference until we get to a very high pressure, but the attraction part is the main part which change the gases from ideal behavior to real behavior. Now just a quick question. Which gas produce less pressure with TV and number of mole constant? The first one is methane, which is a small molecule and non-polar. And the second one is water, which is a small molecule too, but there is a polar interaction. First we need to obtain the size of A and B and then predict which would be produce lowest pressure. If methane is a small molecule and non-polar, that means the A and B constant, it would be a small, and as we can see here, it's relatively a small attraction correction, and B is very small because it's relatively a small molecules. Water is also a small molecules. B should be some small number. The big difference will come with when there was A, because water is polar and it can make hydrogen bond, then intermolecular interaction unit is higher for water in compare with methane. So if we put larger A here, same number of mole and temperature and volume, this subtracted component for water, it should be higher for water in compare with methane. That means the pressure exerted by water would be significantly lower pressure than ideal pressure. So far we talked about equation of state for ideal gas law and van der Waals equation of state for real gas. There are different kind of equation of state. We can categorize them as four set of equation. The first of these are cubic equation of state. Cubic equation of state are an attempt to expand the form of ideal gas law to meet other non-ideal gases. And there is a whole family of these, but van der Waals, Soredlak, Wang, and Payne-Robinson are the most common of those. And then we have real equation of state. Real equation of state are going to be purely theoretical, and the third one is empirical equation of state, are purely curve fitting to match data. Benedict Webb-Robin equation of state is one of the examples for the equation of state, for this kind of equation of state. And finally we have generalized gas law, which is another attempt to generalize ideal gas law for non-ideal gases. The cubic equation of state is the ones that are probably most often used in simulation software. Cubic equation of state expanding ideal gas law to reflect the realities of why real substances are not ideal gases. So for instance, one of the issue is the molecules are attracted or repulsed from each other, and in ideal gas they just totally ignore each other. So as we said before, if we want to deal with the attraction of molecules, we need to adjust the equation. Another issue is molecule in ideal gas law round and doesn't have any volume. Real molecules tend to be not a sphere, so we need to deal with the shape, and they take up space. The volume is not zero, So to account for this thing, we need to modify the ideal gas law. The first one of this cubic equation of state which we talk about it is van der Waals equation. To adjust for the molecules, here is the equation. He has B term here, also have attraction of each other, the A times n square over V square added to account for the attraction between molecules. But why this is a cubic equation of a state? Why we name this type of equation cubic equation? If we notice, we have one term V square and denominator, and the other one has V minus B. If we you to clear this fraction, multiply both sides by these common denominators, I would see that I have V squared times V minus B, which leaves V cube, and other terms of polynomial, so it is cubic in variable V. The two cubic equation of a state that is currently most often used are Sourad one, usually just SRK equation, and Peng-Robinson equation. There are similar to the van der Waals equation. RT over V minus B is similar for all of them. There is an extra term in SRK alpha, which is function of temperature and eccentric factor, which is a correction for shape of gas molecules. By definition, all sphere molecules have zero eccentric factor, and eccentric factor is calculated based on this equation. Omega is equal -1 minus logarithm of p reduce, which p reduce is p divided by p critical at saturated condition, and p reduce at saturated condition, and t reduce equal 0.07. And in denominator, instead of V square, we have a little bit of contribution of size of particle. Peng-Robinson is a different way of doing that. Both of them are very good and especially popular in oil industry for modeling the system there. And now let's look at a little bit further at Peng-Robinson equation. It is similar to Redlich-Wang because it's a modification of Redlich-Wang equation of a state. It's gonna to taking account the critical properties of the substance and eccentric factor, and if you approaching critical condition still is valid, and must be able to use in mixture. It's not just for pure substance. The equation have a lot of parameters. For example, A and B is calculated by this equation based on critical temperature and pressure, and we have alpha, which is a correction to the volume, and inside the alpha we have T reduce, and K, which is the K is dependent on the eccentric factor, which describe the shape of molecules. Now I'm going to talk about virial equation. The virial equation of a state is based on a statistical mechanical theory. It is purely theoretical hypothesizing. As you can see, in virial equation of a state there are second and third virial coefficient and continuous. However, after the third one, it doesn't use too much. The second virial coefficient consider interaction between two molecules, and the third virial coefficient is consider interaction between three molecules. Now I'm going to start from the van der Waals equation to find the relation between van der Waals and virial equation. And the equation is often written in terms of the molar volume, which is volume divided by number of mole, divided both sides by RT, and multiplied through by molar volume. and then divided the first term in the right hand side of the equation by molar volume, we can obtain compressibility factor based on van der Waals equation. If the molar volume is very larger than B, according to the Taylor series, we can rearrange the van der Waals equation in the same form as virial equation. Therefore, second virial coefficient B is related to the van der Waals coefficient A and B. That means both attraction and repulsion considered for second virial coefficient. Good news about virial equation is for so many of substance B and C is well established. The value of B at different temperatures for argon are shown in this table. Statistical mechanics give equation relating the virial coefficient to the potential energy of intermolecular forces, where U is intermolecular potential. At higher temperature, the repulsive forces dominate, then B is greater than 0. And if attractive forces are dominate at lower temperatures, then B is smaller than 0. As I said in previous slide, once Vm is very larger than B, according to the series, we can rearrange van der Waals equation in the form as virial equation. Therefore, second virial coefficient is related to the van der Waals coefficient A and B. Another types of equation of state is empirical equation. The empirical equation which is most cited is Benedict Webb-Robin. This one attempt the virial equation to data. This is an adoption of virial equation to fit real life data. As you can see, there are 8 experimental constants in this equation. This is difficult to calculate or find all the constants, but it is very good for model because it's gonna to prove the model. And finally, let's look at the generalized compressibility chart. As you can see in this graph, we have Z versus P reduced at different T reduced. What people find over the years, no matter which substance, the graph had very much the same shape. And you can see with having reduced pressure and reduced temperature, we can obtain compressibility factor which is on top of each other for different substances. What we talked so far, whenever the compressibility factor turn out to be close to 1, we say the substance is ideal gas. But if it is not close to 1, we use the Z, which is not close to 1, to modify the ideal gas law. It's gonna the temperature side of ideal gas law. So PV is equal Z nRT if you use total volume, and PV equal ZRT if you use molar volume. So this video was a brief description of equation of state. Thank you for your patience and listening.